I received a request to make a tutorial on using stepper motors with the Raspberry Pi. Stepper motors are a broad topic, so I'm going to focus on bipolar stepper motors because they're generally more efficient than comparable unipolar motors, and they have a lot of popular applications. This video will cover a lot of information quickly, but all the code, notes, resources, and more will be available on my website, and as always, a link will be placed in the description. Here's a collection of stepper motors that I recovered from e-waste. This stepper is from an inkjet printer. This one's also from an inkjet. These larger ones are from a laser printer. This stepper is from an old 5 1/4 floppy disk drive. It has 5 wires, so it's unipolar. Later I'll show how to convert it to bipolar. Attached to this CD-ROM tray is a little stepper motor with a lead screw which drives a linear slide back and forth. In a previous video I discussed brushless DC motors whose traits include reliability, quick acceleration, high-speed operation, and high power density, which makes them very popular for drones and RC. Stepper motors are brushless in DC, but their rotation is divided into a distinct number of steps which provides very accurate positional control and repeatability. This makes them very popular for 3D printers, CNC routers, and robotics. Here's my Romax CNC router. The router's Z-axis lead screw is powered by a NEMA 23 bipolar stepper motor. NEMA just refers to the dimensions of the face plate. NEMA 23 indicates 2.3 by 2.3 inches. The Y-axis also uses a NEMA 23. Both have a holding torque rating of 570 ounce-inches. This measure of strength means the stationary motor can hold a weight of 570 ounces on a 1-inch radius pulley. Holding torque assumes the motor isn't turning. When a motor turns, its torque reduces. The faster the motor rotates, the less torque. The stepper motor datasheet should provide a torque versus speed curve, which is helpful in selecting a motor. My router uses Gpio stepper drivers, 1 per axis. They're pretty expensive. When I got the machine in 2010, there weren't many good low-cost alternatives. But thanks to the growing popularity of CNC and 3D printing, the prices have fallen substantially. Here's a DRV8825 stepper driver breakout board designed by Pololu Robotics. You can get clones on eBay for a couple dollars, or if you need more reliability and fantastic support, you can buy them directly from Pololu for a few dollars more. They're not as powerful as the 7M Gecko drives, but for the price you get a lot of power. This board can drive a single bipolar stepper motor at up to 2.2 amps and 45 volts. The maximum current output is adjustable, which lets you use voltages above the stepper motor's rated voltage to achieve higher stepper rates. This is often called the chopper driver. It has over temperature, over current, under voltage, short to ground, and short load protection. There are 6-step resolutions from full step to 132 step, and it has a built-in 3.3 volt regulator, which makes it very easy to interface with the Raspberry Pi. Connecting the DRV8825 is very simple. The minimum wiring requires only 2 Gpio pins, actually 1 if you don't care about direction. The step pin is connected to Gpio 21, and the DIR or direction pin is connected to Gpio 20. You can use any Gpio pins since they'll be specified in the code. The logic ground pin is connected to a ground on the Pi. No logic voltage supply is required because the DRV8825 has a built-in voltage regulator, but the RST or reset and the SLP or sleep pins need to be pulled high by connecting them to a 3.3 volt pin on the Pi because their default low states are to reset and sleep. The EN or enable pin defaults to enable, so it can be left disconnected. The DRV8825 requires a motor power supply between 8.2 and 45 volts. I'll be using a bench power supply because the Pi cannot supply enough voltage and probably not enough current. Make sure the power supply is off before connecting. The VMOT or motor positive pin is connected to the power supply's positive terminal. The motor ground pin is connected to the supply's negative terminal. There's no reverse voltage protection, so double check your connections. The DRV8825 is susceptible to destructive voltage spikes. To protect the board, try to keep the motor power leads short, and it's very important to put a minimum 47 UF electrolytic capacitor across the motor supply as close to the 8825 as possible. I'll use a 100 UF cap. Put the cap's negative terminal on the ground side. The negative side is identified with a vertical stripe. I usually pick a cap with double the voltage rating. For example, on a 12 volt power supply, I'd use a cap rated for at least 24 volts. The optional FLT or fault pin is left disconnected. It's used to detect overcurrent events or thermal shutdown. On a breadboard I have a DRV8825 stepper motor driver breakout board. I'll be connecting it to the Raspberry Pi 3. First, the logic ground is connected to a ground rail, which will later be connected to a ground on the Pi. It's not necessary, but also connect the motor ground to the ground rail just to make sure there's a good common ground. The breadboard's banana plug binding posts will be connected to a bench power supply. The black post is connected to the motor ground. The red post is connected to VMOT, the motor positive. Be very careful when connecting the motor positive supply. The motor power supply will be running over 8.2 volts, which will probably destroy your Raspberry Pi if it came into contact with any of the pins on the Pi. In other words, please make sure the motor power supply positive wire doesn't touch anything but the DRV8825's VMOT pin. A 100 microfarad cap is placed across VMOT and ground to protect the board from LC voltage spikes. Again, the stripe side of the cap should be on the ground side, as close as possible to the VMOT and the ground pins. Please note that the electrolytic caps can explode if you put them in backwards. The sleep pin is connected to a 3.3 volt rail, which will later be connected to a 3.3 volt pin on the Pi. This pin could also be connected to a Gpio if you wanted to be able to put the driver to sleep to save power, which could come in handy because stepper motors use a substantial amount of power even when not turning because they have a holding torque. The reset pin is pulled high, which is necessary for the driver to operate. The step pin is connected to Gpio 21. When the pin is pulsed, the motor will take a single step. The direction pin is connected to Gpio 20. This will allow the Pi to change the motor direction. Finally, a 3.3 volt pin on the Pi is connected to a 3.3 volt rail on the breadboard, and a ground on the Pi is connected to the ground rail. Next, the breadboard is connected to a variable bench power supply, red to positive and black to negative. I'll set the supply to 12 volts. I'll switch on the supply and plug in the Raspberry Pi so the maximum current can be set, which is important to do before connecting the motor. The Vrf Potentiometer is used to set the maximum motor current. Turning the pot changes the Vrf or voltage reference. This voltage can be measured using the Vrf via or on the pot itself. The DRV8825 has a simple formula to calculate the maximum current from the Vref. Maximum current equals twice the voltage reference. For the first example, I'll use a laser printer stepper motor, which according to the datasheet has a peak current limit of 1 amp. Half of 1 amp is 0.5, so the Vref should be set no higher than 0.5 volts. Although according to the DRV8825 datasheet, if you're running in full step mode, the driver will cut current to 71%, so I could go a little higher if I need the extra torque, as long as I stick to full step mode. Please note that the coil current can be significantly higher than what is displayed on your bench power supply because the DRV8825 steps down the voltage. Therefore, you should always use Vref to determine the current limit and not the bench supply. Back on the breadboard, I connect the negative multimeter probe to the ground rail. The meter is turned on and set to read voltage. Touching the pot with the positive probe indicates about 1.4 volts, which equates to 2.8 amps. This is way too high and would probably fry both the driver and the motor. An alligator clip is connected to the positive probe. The other end is clipped onto a small metal screwdriver. Now when I turn the pot, I can also read the Vref. Turning the pot clockwise lowers the Vref. 0.5 is the maximum, but I'll be conservative and go a little lower, which will save electricity and keep things running cooler. Around 0.43 sets the current limit to 0.86 amps, or about 86% of peak, ignoring the 71% limit in full step mode. I can always increase it if I need more torque. Before connecting the motor, it's important to turn off the power supply. Connecting or disconnecting a stepper motor while the driver is powered can damage the driver. A bipolar stepper motor has 2 coils with 2 wires per coil. The pair from one coil is connected to A1 and A2, and the other pair is connected to B1 and B2. The stepper motor wires are often not labeled. One easy method to identify which wires go to which coil is to use an LED. The LED is placed across the first 2 wires, purple and white. Direction doesn't matter. When I spin the motor, the LED blinks. This indicates that purple and white are a coil. When the LED is placed across the white and the black wire, and the motor is turned, nothing happens, which is expected because the white and black are on separate coils. Just to be sure, I'll place the LED across red and black. Turning the motor confirms that these wires comprise the second coil. Before connecting the motor, I'll remove the power supply plugs to ensure nothing gets fried. A black nylon tie is wrapped around the motor gear to make it more visible. A motor coil pair is connected to B1 and 2 on the DRV8825. The other coil pair is connected to A1 and 2. It's now safe to reconnect the motor power supply. According to the datasheet, this is a 24 volt stepper motor, so I'll set the power supply to 24 volts. Okay, we now have the minimum hardware configuration to run the motor. Before running any software, please make sure the Pi is up to date with sudo apt-get update and sudo apt-get upgrade. As always, I recommend you start with a freshly wiped Pi using the latest version of Raspbian Jessie to ensure you have all the necessary software. In idle, I have a blank Python file. From time, sleep is imported. From rpi Gpio, Gpio is imported. A few constants are declared. dir will be the direction Gpio pin 20. Step will be the step Gpio pin 21. CW is 1 for clockwise direction. CCW is 0 for counterclockwise direction. SPR is 48 for steps per revolution. The laser printer stepper motor datasheet shows a step angle of 7.5 degrees. 360 degrees divided by 7.5 equals 48. Therefore, 48 steps will rotate the motor shaft one full circle. The Gpio mode is set to BCM for Broadcom numbering. Gpio Setup sets the direction pin to an output. Setup is used again to set the step pin as an output. Gpio output sets the initial direction to clockwise. The step count for the first test will just be one rotation, so it's set to SPR. The delay is set to 0.0208, which is about 1 second divided by 48. A for loop counts the 48 steps. First Gpio output toggles the step pin high. There's a 0.0208 second delay. Then output is used again to toggle the step pin low. There is another delay and the loop continues. These 4 lines just pulse the step pin. Since there are 2.0208 second delays, the 48 step loop should take approximately 2 seconds to complete, although the Python sleep method is not very reliable. After the loop completes, the program pauses for half a second. Then output is used to change the direction pin to counterclockwise. It's not very dry, but to save time, I'll just paste another copy of the first loop. This will spin the stepper around again, but this time it'll be traveling counterclockwise. Okay, I'll run the program. The motor's spinning. There's the first loop, and the second loop takes it backward. The motor bounced around a bit, mainly because I only have a piece of tape holding it in place, but also because 48 steps per revolution is not a lot of steps. This results in jerky motion, which causes noise and vibration, especially at slower speeds. This can often be mitigated by using microstepping. I don't want to spend too much time explaining stepper motor theory. Instead, I found this great website by Nanotech that has many interactive animated examples. I'll put a link on my website, along with a bunch of other great resources. On the site, I scroll down and from the stepper motor menu, select Bipolar 4-lead. There's an explanation of 4-lead bipolar control. Clicking Phase Schema shows the direction of current flow through the coils at each step. Currently it's set to half step. I'll switch to full step. Now clicking the right arrow cycles through the steps. This simplified representation gives a clear example of how the driver powers the coils to make the rotor turn. A stepper motor may have any number of coils, but they are connected in groups called phases. All the coils in a phase are energized together. 4-wire bipolar stepper motors are 2-phase and have 2 groups of coils. Switching to half step causes the driver to alternate between driving both phases and driving a single phase. This doubles the resolution of the motor by adding 4 steps per cycle. However, there is a reduction in torque because half of the time only one group of coils is acting upon the rotor. Next, from the stepper motor menu, I'll select microstep. Now the step operations have varying current ratios between the phases, which can give even greater resolution. When I click the right arrow, the rotor steps are now much smaller than before. This example is demonstrating 32 microsteps. The cycle now takes 32 steps to complete. I recommend you check out this site and play around with the different modes. It's a great learning tool. The M0, M1, and M2 pins from the DRV8825 are connected to the Pi's Gpio 14, 15, and 18 respectively. This will allow the Pi to programmatically set the DRV8825 stepping mode from full step to 32 microstep. In the Python program, a mode constant is set up for Gpio pins 14, 15, and 18. Gpio Setup sets the 3 mode pins as outputs. A resolution dictionary will match the microstepping modes to the corresponding Gpio pin pattern as designated in the DRV8825 datasheet. Full is 3 lows, half is high, low, low, and so on. Gpio output sets the mode to half step. Now when I run the program, the motor is turning and it's a little quieter. Notice that it only made a half turn. This is because there are now twice as many steps per revolution. Set of 48, it now takes 96 to make a full circle. To adjust for the half step mode, the step count is doubled by multiplying the SPR times 2. It's also necessary to adjust the delay because doubling the steps will double the time required. Therefore, the delay is divided by 2. Let's try again. Now the motor makes a complete revolution in the same amount of time as before. It's still a bit noisy, so let's see if we can smooth it out a bit more. In the code, I'll change the resolution from half to 132. The step count now needs to be multiplied by 32, and the delay needs to be divided by 32. This should result in a single revolution in the same amount of time as before. I don't know if you can tell in the video, but the motor is now whisper quiet. I'll run it again. Before the motor was bouncing around the table, now it's standing very still. Despite these promising results, it's important to note that there are some significant downsides to microstepping. There's often a substantial loss of torque which can lead to loss of accuracy. For more info, there's a white paper on my website that details the myths and realities of microstepping. Now let's take a look at the little CD drive stepper tray. The LED coil test doesn't work on this motor because it doesn't generate enough power to light the LED. Instead, I'll use a multimeter set to continuity. Touching the first two pins gives a beep which indicates a coil. The first and third pins are open, as expected. 3 and 4 also gives a beep because they are the second coil. So pins 1 and 2 are a coil, and 3 and 4 are a coil. I already went ahead and lowered the maximum current down to 500 milliamps as per the CD stepper motor datasheet. It also indicates that this is a 5-volt motor. The DRV8825 requires a minimum of 8.2 volts, but this is not a problem because the DRV8825 will step down the motor voltage to ensure the maximum current is not exceeded. Therefore, I can run the power supply at 12 volts and the motor will be okay. With the power supply disconnected, I can connect the CD tray motor coils to the DRV8825 B1 and B2 pins and A1 and A2 pins. Then reconnect the power supply. In the program, SPR is changed to 20 because this is a 20 step per revolution motor, or 18 degrees per step. I'll leave the microstepping set at 132. The step count is multiplied by 8 because I've determined that it takes 8 turns of the lead screw to slide the tray from one end to the other. The full step delay is also decreased to 0.005 to speed up the demo. Divided by 32 will give a delay of about 156 microseconds. The minimum possible delay for the DRV8825 is 1.9 microseconds per high and low pulse. The motor drives the lead screw which quietly slides the tray back and forth. This is a good example of converting rotational motion to linear motion. Now let's take a look at the old 5 1/4 floppy drive stepper motor circa 1985. It has 5 wires, therefore it's unipolar. Let's take a look inside and see if it can be converted to bipolar. Please note that some stepper motors can be permanently damaged by opening them up. Opening a motor can lead to demagnetization of the rotor. This can result in a substantial loss of torque. I've seen some debatable data that suggests this only applies to permanent magnet stepper motors using aluminum nickel cobalt magnets. According to the manual, this floppy motor is a hybrid design which tends to use a more resilient neodymium iron boron magnet. But remember, I got this motor for free. I wouldn't open any expensive stepper motor without first checking with the manufacturer. Bipolar stepper motors are called bipolar because current needs to alternate directions across the coils to change the magnetic poles. This changing polarity requires a more complex driving circuit. Conversely, unipolar motors have a center tap per phase. This splits the coil into 2 sections. Each section of the winding is switched on for each direction of the magnetic field. This requires a simpler driver circuit. However, this also results in a substantial reduction in torque because only half of the coil is energized. 6-wire unipolar motors can often be used in bipolar configuration by ignoring the center tap wires. However, the 5-wire versions like the floppy motor have both center tap wires connected together. To use them as bipolar, this connection needs to be severed. Then the center taps can just be ignored. The case is on pretty tight. Probably hasn't been opened since it left the factory over 30 years ago. Okay, it's apart. Here's the rotor. It probably would have been better if I'd only removed the other end and had left the rotor inside the stator, in case I'm wrong about the demagnetization. There are several coils, but remember, a stepper motor may have any number of coils, but a bipolar design only has 2 phases, and all the coils in a phase are energized together. The coil wires are terminated at the 5 large solder blobs. One of these blobs contains the center taps. The meter is set to ohms to determine the center tap. Resistance between the center tap and a coil end should be half the resistance found between 2 coil ends. The first 2 read 144 ohms. The third is 72 ohms. Since it's half, it should be the center tap. Just to be sure, the fourth is 144 and the fifth is 144 too. Therefore, the third is definitely the center tap. I went ahead and separated the 2 center taps from each other. Here's the center tap wires under a microscope. There are 4 hair-like wires. Each pair is a coil center. I removed 1 pair from the solder pad and resoldered them together. The motor now can be used with the bipolar DRV8825 driver. The floppy motor ribbon cable coil order is different from the 2 previous motors, so I'll extend the motor A and B pins with some jumper wires in the correct order. I can now connect the floppy motor. I already cut off the 5th unused center tap wire. For the next example, a switch will be added to change direction. One terminal of the switch goes to Gpio 16, another terminal goes to ground. Flipping the switch will ground Gpio 16, which will change the pin state from high to low or 1 to 0. One issue with the last program is that it relies on the Python sleep method for timing, which is not very reliable. For the next example, I'll use the Gpio library, which provides hardware-based PWM timing and is included with the latest release of Raspbian Jessie. From a terminal, type sudo pygpiod. This starts the Gpio daemon, which must be running to use the library. Time sleep will be imported, but only used for the main loop, not for the step timing. Gpio is imported. The same constants for direction and step are used, and a new one for switch is added and set to Gpio 16. A pi is instantiated to connect to the Gpio daemon. Set mode sets the switch Gpio to an input. Set pull up down turns on the switch's pull up resistor so the pin doesn't float. Set PWM duty cycle sets the step Gpio to 128, which is 50%. This means the step pulse will be high 50% of the time and low 50% of the time. In other words, equal lengths for high and low. Set PWM frequency sets the step pin pulse frequency, 500 for 500 Hz, or pulses per second. The Gpio library uses a hardware-based PWM clock, which is much more accurate than the software-based Gpio library. It can also be used for every Gpio pin. However, it is limited to specific frequencies per sample rate, as specified in this table. You can change the sample rate using the TAC-S configuration option when you start the Gpio daemon. The default sample rate is 5, which has values between 8,000 and 10 Hz. For this example, I chose 500, which is one of the values. If I had specified 600, it would have automatically dropped it down to 500, or 700 would have been bumped up to 800. If you need to use a frequency not found in the table, Gpio also allows you to use the Pi's built-in hardware PWM, which is only available on Gpio pin 18. Instead of the set PWM methods, you'd use the hardware PWM method. It takes parameters for Gpio, frequency, and duty cycle. A try statement wraps the main loop, which is an infinite while. The PWrite method sets the direction Gpio pin to the value of the toggle switch. The PWread will either be 0 or 1, which corresponds to clockwise or counterclockwise. A 0.1 second sleep is added to not tax the CPU, then the loop repeats. Another advantage to this approach is that the PWM motor control does not block the program loop. You could add more code to this loop, and the pulses should not be affected, unlike the previous example which relied on the Python sleep for PWM. Finally, an accept will catch a Control-C break and gracefully exit the program. Set PWM duty cycle turns off the PWM, and stop releases the Gpio resources. I'll start the program. The motor is spinning counterclockwise. Flipping the switch toggles the motor direction to clockwise. One drawback to this example is we only have control over speed and direction. It doesn't afford the ability to specify the number of steps to travel. Also, switching a motor direction abruptly or accelerating too fast can lead to missed steps. A better practice is to smoothly accelerate and decelerate. This is often referred to as ramping. Both of these issues can be addressed with Gpio waveforms. I rebooted the Pi. Currently there is a bug in the Gpio library related to waveform timing. I'll start the Gpio daemon, but this time the TAC-T option is used to set the clock peripheral to 0 for PWM as opposed to the default PCM. This fixes the waveform timing. Hopefully this bug will be fixed pretty soon. Also note, this workaround would interfere with the PW timing in the previous example. Back in idle, I've made a few changes. Set mode is used to set the direction pin to an output, and again to set the step pin as an output. I found the method generateRamp from a post on the Raspberry Pi forum by Joan, the author of the Gpio library. Don't worry if the method itself seems complicated, because it's very easy to use. The method takes a variable ramp, which is a list of frequency and step pairs. I made a few changes to the method. I added wave clear to dispose of any pre-existing waveforms, and hard-coded the Gpio step pin. Length is the number of ramp levels. Each level is a pair of frequency and steps. WID is a list to hold the wave IDs. A for loop iterates through the ramp levels. Frequency holds the frequency specified for the current ramp level. Micros is the number of microseconds for the pulses. 500,000 microseconds is half a second. Divided by frequency gives us the length for the on and off pulses. WF is a list to hold both the on and off pulse. Append adds a Gpio pulse. The first parameter is the Gpio pin to turn on, the step pin. Instead of just specifying the Gpio number, you have to use rather an unintuitive convention, which is 1 left shifted to the Gpio pin number. The second optional parameter allows you to turn off a pin. 0 is used since it's not necessary. Micros is the length of the pulse. This is the on pulse. Another append adds another pulse. This time the on pin is omitted and the step pin is turned off. This off pulse is the same length in micros as the on pulse. Wave add generic adds the current pulse list to the current waveform. Wave ID is stored by wave create, which creates a waveform from the data provided by the prior wave add generic call. Next, the waveforms are chained together. Chain is a blank list to hold the chains. A for loop iterates through the ramp levels again. The number of steps is retrieved for each ramp level. X and Y are just another unintuitive convention to translate the number of steps into the data format required for chaining. The chain list is appended. 255,0 indicates a loop start. A wave ID is specified. 255,1 indicates a loop repeat. X and Y are the number of steps. Basically, each chain is just a command to send a wave at a given frequency for a specified number of steps. Finally, wave chain transmits the chain of waveforms. The main program is wrapped in a try. Old ramp holds the previous switch state. An infinite while loop. New ramp retrieves the current state of the toggle switch. If it's changed from the previous value, the state is checked. True indicates a ramp up. The generate ramp method is called with a list of frequency step pairs. 320 Hz for 200 steps, 500 Hz for 400 steps, 800 for 500, 1000 for 700, 1600 for 900, and finally 2000 Hz for 10,000 steps. This will very gradually accelerate to 2000 Hz. The number of steps is exaggerated for demonstration purposes. Often a specific frequency will cause resonance, and it's necessary to increase the acceleration to go through the resonance frequency quickly. Else if the switch is in the other position, a ramp down is transmitted. Generate ramp is called with 1600 Hz for 900 steps, 1000 Hz for 700 steps, 500 for 500, and 320 for 400. Old ramp stores the current state. The program sleeps for 0.1 seconds and repeats. Again, except catches Ctrl-C and gracefully exits. Wave clear clears all waveforms, and PyStop releases resources. This program will ramp the stepper motor up to 2000 Hz and back down when switched. For this demo, I'll use an inkjet stepper motor, which has 96 steps per revolution. 2000 Hz divided by 96 SPR times 60 seconds gives us 1250 RPM. I tried switching this motor from off directly to 1250 RPM, and it was very unhappy. It just made a loud whine and it didn't turn. Kind of like popping the clutch in a sports car, which just spins the tires instead of maximizing acceleration. Let's see if ramping works better. I attached some black gaffer's tape with a reflective sticker to the inkjet motor. A laser tachometer is mounted above. Sorry the display is upside down. I'll also show the frequency on an oscilloscope. Flipping the switch starts the ramp up. The motor easily accelerates up to exactly 1250 RPM. Toggling the switch ramps down, a gradual deceleration. One more ramp up. Note the scope shows the increasing frequency. I hope you found this video helpful. You can support this channel by subscribing, leaving a like, and sharing. Thanks for watching.